All right, next example, we've got example 11. The integral from 1 to infinity e to the negative x over x squared plus 1. So what I'm going to go ahead and do for this one is I am just going to think about, let's take e to the negative x. Let's start with that. Now e to the negative x is definitely going to be bigger than or equal to itself divided by some number. Because x is going from 1 to infinity, the denominator here, x squared plus 1, has to be a number bigger than 1. So anything divided by a number bigger than 1 has to be less than the original. And we're not dealing with anything that is 0, so this is definitely not going to be negative. So right there is our inequality for the comparison theorem. So then, this is the integral. The integral of this function is what we're trying to figure out. So that means we should figure out what the integral of this function does. Does it converge or diverge? Well, we know, let's go ahead and write this out. Actually, we're ready to go. I'm going to write it out since this inequality and the integral from 1 to infinity of e to the x dx converges. How do we know this? Well, you can see example 10, the previous problem. That's exactly this integral right here. It equals 1 over e, so that converges. So this integral converges by example 10. So must the integral from 1 to infinity e to the negative x over x squared plus 1 dx. Sometimes these problems are exceptionally quick. Not always, but sometimes they are, such as this one. Okay, moving on to the next example, example 12. All right, natural log of x over the square root of x integrated from 1 to infinity. So again, a very common trick here is to take the sort of more complicated looking function, natural log of x, and say, hey, if we take that function and we divide it by this quantity, square root of x, it will result in something that is smaller than the original. Now this is only true if what we're dividing by is a number that is less than 1. Excuse me, sorry. This is only true if it's greater than 1. It's not true if this number is less than 1. For instance, the square root of a half, this is less than 1. So if we divide something that's less than 1, we divide by something that's less than 1, I should say, the result is something greater, right? 4 divided by 9 halves is actually 4 times 2 9ths. I meant to say 2 9ths here. I'm all over the place, right? If I take a number and I divide it by a number that's less than 1, such as 2 9ths, then division by a fraction is multiplication by its reciprocal. We end up getting something that is bigger than the original number. But notice our range for x starts at x equals 1. So no matter what values get fed into this, we are definitely going to have something that is greater than or equal to 1, so there's no issues there. Okay. And then as well, is this negative? Is it actually true that this is greater than or equal to 0? Yes. Why is that? Well, the natural log of 1 is equal to 0, right? So on our graph, natural log does this. So right here at x equals 1, if you plug in any values of x less than 1, the natural log is negative. But from this point forward, the natural log of x is positive if x is greater than 1. Or equal to 0 if x is greater than or equal to 1. So this inequality does work out. No issues there. Okay. So there's another way that we can think about this, perhaps, and that is, let's see, is this going to help us as written? Well, possibly. We would have to integrate this sucker, which is not terrible, but not great. So let's see if we can think about it in a slightly different way. What I did was I started with this quantity right here. Sorry, I started with this quantity here, and I divided by square root of x in order to make this quantity smaller. Okay? But there's another inequality that we can think about, sort of the opposite inequality. And that is, start with the square root of x. And then think about it. If I multiply this by the natural log of x, do I get something bigger? Do I get something bigger? Well, depends on what you multiply by. If the natural log of x is greater than 1, if it's greater than 1, then this would be true, right? If it's greater than or equal to 1, that would be true. But when is this true? Let's return to the natural log graph. Natural log of x looks like this. So we know this value right here is x equals 1. So that means the y value is 0. So we want to know, where does this happen? If this is y equals 1, let's say the y values are given by natural log of x, we want to know, where does this intersection happen? The natural log of what number is equal to 1? Well, e. Natural log of e is equal to 1. So this is x equals e, which is about 2.718. So the natural log of x is not always greater than or equal to 1. So this natural log of x, this caveat here, is only valid if x is greater than or equal to e, which, just for reference, again, is about 2.72. I'm going to round to the nearest hundredth. Now look at our integral. We have 1 to infinity. So we might actually have to break this up. We might have to break this up. So let's clean this up just a little bit here. And let's hold on to this for now, but I don't think we're going to use it. So let's just go with this inequality. So we'll say if x is greater than or equal to e, then this inequality that we have is true. Furthermore, we can say that it is greater than or equal to 0, which we need for the comparison test, so I'm just, always including that. So this suggests that we should take our integral from 1 to infinity, natural log of x over square root of x dx, and we should split this up into the integral from 1 to e, natural log of x over root x dx, plus the integral from e to infinity of natural log of x over square root of x dx. This first integral right here we know converges because the natural log of x over square root of x is continuous, and the domain of integration, the interval from 1 to e, is bounded. It doesn't extend to infinity, and our function doesn't, its value doesn't approach infinity or negative infinity. Those two things together ensure that we have a finite area. So this converges, and again I'll say because ln of x over root x is continuous, and the interval from 1 to e is bounded. So then this integral that remains, we can use comparison on that. Since for x greater than or equal to e, we have the inequality 0 is lesser than or equal to square root of x, which is less than or equal to the natural log of x over square root of x, and the integral from e to infinity of 1 over the square root of x dx. Well, this is really the same thing as x raised to the 1/2 power. So here we have a large interval, an unbounded interval, so a big interval, but we've got the small p, a p-value less than 1, less than or equal to 1. So this means this integral diverges. P is equal to 1/2, which is less than or equal to 1. So since that integral diverges, it doesn't actually matter that this integral converges. The convergence and divergence, they don't undo one another. This is essentially saying the area underneath this curve is some number, some finite number. Let's say it's 7. But the area underneath this curve is infinity. Well, 7 plus infinity is still infinity. So the integral from 1 to infinity of 1 over, not 1, natural log, excuse me, square root of x dx diverges by comparison.